So thank you thanks the organizers for the invitation, and thank you for coming. So I will talk about maximally hypoelliptic differential operators. I will start the talk with very elementary things. Usually in my talks, sometimes I give the talk in front of people who don't do differential operators, and so I never get the opportunity to present some of the main ideas of the proof of our theorem, of the main theorem, which I'll present at some point. And so I really want to do this today. So I will present the main ideas. I will not, of course, present the proof, but the main ideas behind the proof. There is a very cool trick at the very end. So if you stay at the end, you get rewarded with a cool trick. Even if you don't listen to 2/3 of the talk, I will say that here is the cool trick, so you can even just ignore that part. But eating dessert without lunch is silly. So, the goal is to solve. So if you have a linear differential equation, there are two questions you can ask. Can I find a solution? And the second question is, are all solutions smooth? That's the two most natural questions you can ask. And I'm interested in the second question, which is, are all solutions smooth? They are related to each other. Usually, if you can solve one of them, you have some guess how to do something for the other. So I have an M smooth manifold, and I have D, a differential operator. So it's a linear map from C infinity functions to C infinity functions. So this is a map which is written locally as some differentiations. And since it's written locally using differentiation, it's linear, I can extend it to distributions. And I really like C minus infinity for distributions. Okay? And so definition, we say that D is hypoelliptic So for any distribution, if it happens that its image is smooth, then the original distribution is smooth. Okay. So in other words, I said I'm interested in this equation. And usually I start with V, which is a smooth function. I'm looking to find U. And so this tells me that if I succeed at finding U in the space of distributions, then U is in fact smooth. So examples. I will start the silly example, the most not so silly, but so d over dx on R. This is hypoelliptic. This is the fundamental theorem of calculus. If I start with a smooth function and integrate it, that's smooth. The other silly example, which is on R2, this is, of course, not hypoelliptic. I could take any distribution which doesn't depend on x and its derivative is 0. Now, these two examples are not very interesting. The two examples which are very interesting is the Laplace operator on Rn and the Cauchy-Riemann equation. So minus d over dx with I plus d over dy on R2. I think that's correct. So this is the Cauchy-Riemann equation, and this is a Laplace operator, and both of these are hypoelliptic. And so if I look at this equation, du is equal to 0, I will, for the rest of the talk, I will call U a solution of the equation if it has this property. So this one, solutions of it are constant functions, not so interesting. They satisfy all of the properties you can imagine in the world. This one, as I said, is not hypoelliptic. But these two, they have a lot of very interesting properties. One of them, we are all very surprised when we take complex analysis course by how many properties analytic functions satisfy. One of them is Cauchy's integral formula. So if f is analytic, the entire then the nth derivative at 0, I write it in the simplest form, 2 pi I, the integral over the unit circle of f of z over z n plus 1 dz. So one of the first surprising results is that the nth derivative can be related to the function itself, which this implies that the nth derivative at 0 is less than or equal to some constant, depends on n, the norm of f c0 on the unit disk. Of course, you can do better, and you can do the unit circle, but for hypoelliptic, I can't do better. Anyway, so this can be generalized for any hypoelliptic differential operators. So you have this theorem, which says that M compact, you can state it also for non-compact manifolds, but let's keep things simple. So M is compact and D hypoelliptic. Then for all n in N, you can find some constant such that for all solutions, so D of f is equal to 0, which doesn't matter if I say they are distributions or not, they are automatically smooth. Then norm of f cn is equal to a constant norm of f c0. And I suppose M is compact, so I don't need to talk about Cn. What Cn is well-defined equivalent. Anyway, so I have this inequality. This theorem is not due to me. I never saw it in a book, but the idea in the proof is more or less in Hormander, and he more or less says it in some remark, cryptic way. I think it was a fulcral result at some point due to Schwartz, something like this. I have 5. So the proof of this theorem is extremely simple, and I love it. I even think that I can give it in an exam. I'm not too sure if I will get fired after, but right? Yes. Ah, you are. Yes, but now you spoil. Okay, so I will give the proof anyway. It's a very simple proof. So the proof is as follows. You take C infinity functions on M, and you equip it with 2 topologies. The first topology, I take this space, and I equip it with 2 topologies. The first both of the topologies are defined using semi-norm. So the first topology is the one which takes a function to Fn for all n. So this gives you the usual standard topology we all know. The second topology is the one which, it's a small twist to this. So you take the C0 norm. I used Cn. So you take the C0 norm and you take these norms. So f maps to the norm of D of f Cn for all n. So the twist is that this one, you take all derivatives. A sequence converges if you have uniform on all derivatives. This one, you still have the C0, but you only take the derivatives which come after taking D. So a priori, this is a weaker topology, but as we'll see, it's actually equivalent. So what can I say? So second topology is weaker than first topology. This is obvious. What's also obvious, C infinity of M is complete with first topology. What's till now I didn't use hypoellipticity. What's not easy but crucial is that the second topology is complete. So C infinity is complete with second topology. Why is this? So I take a Cauchy sequence. So Fn Cauchy, with respect to these semi-norms, the C0 and all of these norms are complete by themselves. So what I get is that Fn has to converge to some function which is continuous, and D of Fn has to converge to some function, and this one is C infinity. And this convergence is in the classical C infinity norm. But then this implies that d of f is equal to g in the sense of distributions. And so I get that f is smooth by hypoellipticity. And so by hypoellipticity, f is C infinity. And this is all I needed, because now I have the point, the limit point is in my space. I have to say, I thought about it. I thought about the organization of the slides. I never noticed that I will have to restart at 2 and not 1. Anyway, so the two topologies are complete. Now we are done with the proof, because you take the identity map from C infinity of M to C infinity of M. So the closed graph theorem. And you apply the Banach open mapping theorem. Usually it's stated for Banach spaces. Here we will use it for Frisch spaces. The same proof works. You only need to apply the bare category theorem that's given by completeness. So what you do is you put here the first topology, and here you put the second topology. And this is continuous because one is weaker than the other. Banach open mapping theorem, and obviously bijective, Banach open mapping theorem gives you homomorphism, so two topologies coincide. And this implies that the semi-norms are connected to each other, which means that there exists for all n, there exists m in n and constant such that for all C infinity functions, whether solutions or not, norm of f Cn is less than or equal to a constant, norm f C0 plus norm d of f Cm. For all C infinity functions, you will have this inequality. But of course, if d of f is equal to 0, well, I get the inequality I was looking for. And of course, this works with C0 here. I could replace it with L2, LP, whatever. I also didn't think of that. So I gave you some reasons why one would care about hypoelliptic operators. So what are the examples of how to prove that an operator is hypoelliptic? Almost always it comes from Sobolev spaces. And essentially, because of things like this, that's essentially the only way to prove hypoellipticity. And so we have Sobolev lemma, which tells us that the intersection of the Sobolev spaces on a manifold are equal to C infinity functions. So the general strategy to prove hypoellipticity is by proving that, so if I can find a function from natural numbers to natural numbers, which is decreasing, increasing, and its limit, is infinity, and I can prove that for every u, du is in Hs, implies that u is in H phi of S. If I can prove all of this, then I'm done. I have hypoellipticity, because if du is smooth, it belongs to all of them, and so u belongs also to all of them because of this. Sobolev spaces are nested, and so I get hypoellipticity. So this implies hypoellipticity, and a very easy observation is that if d is of order n, then of order k, then phi of n has to be less than or equal to n plus k. This process of going from du to u is an integration process. we hope that it is. And so, and it's very easy to see that if D has order k, you cannot do better than this. Okay. And now it turns out that when phi of n is equal to n plus k, we have a very nice characterization using the principal symbol of elliptic operators. We don't have in general even a conjecture on what a classification of hypoelliptic operators look like. We know enough about the problem that we know that it's a very hard problem. But turns out that when you put the best possible estimate, this problem is much easier to solve thanks to the theorem of so we have the following theorem of Kohn, Nirenberg, and Hormander, which is in the 60s. And the theorem is as follows. So if D is of order k on any smooth manifold, then the following are equivalent. So the first one, this condition. So for every u, du is in Hs, implies that u is in Hs plus k. I write S and sometimes. The second condition, for every x and xi, the cotangent bonded away from 0, the principal symbol is non-zero. And if M is compact, this is equivalent to saying that the differential operator from the Sobolev space to this space is fed. Okay, so I'm pretty sure all of you have seen this theorem more or less, but anyway, I write it. And the key point is that this is if and only if you have this condition, if and only if you have this ellipticity condition. Okay? And you have this very nice C-star algebra characterization. And this will be the key point when I go to the next generalization. Now, one observation is that this doesn't cover all hypoelliptic operators. One can create operators which don't satisfy this. The main example is this one, the simplest example of this one. So this one is, of course, not elliptic because of this x term. It's almost a Laplace operator, but with two vector fields, one of them vanishes. So this is not elliptic, but it is hypoelliptic. The way this was proved by Kolmogorov almost 100 years ago now. It was in 1918, I think, something like this. He was doing Brownian motions, and that's, yeah, you are good. You are much better than we had. Yeah, okay. I actually thought it's less. Anyway, yeah, I'm having a hard day. So the way he proved it is he constructed a kernel for this operator, and then you immediately see that from the kernel that the operator, essentially he, like we did with the fundamental theorem of calculus, he solved the differential equation. Now, Poland and Stein noticed in the 70s that actually this approach can be modified to give you hypoellipticity of this operator. So what they did is they argued that there is no reason to use the classical Sobolev spaces. You can modify them a little bit, and you will get maximal regularity for this. So they define the following Sobolev spaces on R2. And I use tilde to distinguish them from the classical ones. So the first one is L2 locally. Hypoellipticity is a local problem, and so one shouldn't use L2 spaces, instead should use local variants of all of these things. So you define the Sobolev space. The first one, just like the usual, and the rest, you define them by recurrence. And so it's u in hk such that dxu and x dyu is in hk. If I remove this x, this is the classical sublove spaces, of course. Okay, and so the motivation is very simple. This is a Laplace operator with two different vector fields. I just take the appropriate spaces, but for these two vector fields. Now the main observation, so we have this obvious inclusion. The old sublove spaces are included in the new one because if I have a some function which is L2 locally and multiplied by x, that remains L2 locally. So this is obvious. What's less obvious is other inclusion. So we start with, we have this inclusion. Why is this inclusion satisfied? This is due to this equation, which is really the key point behind hypoellipticity of this differential operator. So if I write this in more, if I expand this equation, then it says that dx x dy minus x dy dx is equal to dy. Now if I take q, which is in h tilde 2, and I apply this, so this one decreases by 1, so it becomes an h tilde 1. This one again decreases by 1, so this becomes h tilde 0, which is L2. And this will do the same thing, just opposite. So I get from this equation that if u is in h tilde 2, then dyu is in L2 locally. And this is all I needed to get that it is in h1, because dx is free. Dx is actually in h tilde 1. I have much better estimates on dx. It's dy, which I don't have. So I get from this Lie bracket that h tilde 2 is included. So these sublove spaces are not exactly equal to the old one. They intertwine. Anyway, by recurrence, you can easily see that h tilde 2k is included in hk. Let's just repeat. And so you get that the intersection of the new ones, that it will be the intersection of the old ones, which is C infinity. And this is all I needed to use this approach of Cohen, Nirenberg, and Hormander to get hypoellipticity. And then Folland and Stein proved that actually you have the best possible thing. So if you, for this differential operator, for every u, du is in, and for every s, du is in h tilde s, implies that u is in h tilde s plus 2. So a few remarks. Here I define the sublove spaces for natural numbers, but of course you can extend them by interpolation, the usual tricks, to or real values. Here, so I have as if my operator was elliptic. This is false if I use classical sublove spaces, because the previous theorem was if and only if. And so I have this. So this operator behaves as if it was elliptic, but with respect to this scaling of sublove space. Now the idea is very simple. There is no reason in this definition to use these two vector fields. I could use any family of vector fields on the manifold. Of course, I always want the intersection to be C infinity. That plays a crucial role, but I can just use anything. I have 50 minutes, right? Yeah, okay, I'm good. I'm very good. So now we go to the general case. So I have M at smooth manifold. And I just take any vector fields. Then I can define the sublove spaces exactly like I did before. And by recurrence, exactly like before. But of course, I want, as you saw, I need the intersection of all Sobolev spaces to be equal to C infinity. Of course, this is false in general. So I need some conditions, and the way we obtained it here is using the Lie bracket. And so I will suppose what we call the Hormander's condition to get that the intersection of all Sobolev spaces is equal to C infinity functions. And so we have Hormander's condition, which says that for every x in M, the linear span of, I take my vector fields, and I take their Lie brackets. And I take the iterated Lie brackets. The trick that I used with 2 Lie brackets, it also works if I have 3 Lie brackets. It's just instead of having H2 included in H1, I will have H3 included in H1. So there is no reason to stop at 2. Etc. This is the tangent space. And of course, the tangent space is finite dimensional. So if this happens, it only happens for a finite number. So if M is compact, of course, I have a bound. Because hypoellipticity is local, I can force there is a bound. And I would have cheated at some point and suppose there is a bound. Yeah, okay. So if we have this condition, if the Hormander's condition is satisfied, then the intersection of all of these Sobolev spaces is equal to C infinity function. Okay, the argument, just an iteration of the argument I gave before. And so once you have this, the obvious question you can ask is, well, I can use these operators to study hypoellipticity. And so I hope that the hope is that the maximal, the best possible estimate I can ask for, just like for standard Sobolev spaces, I could classify these using the principal symbol. So I ask, can I find a principal symbol which classifies the best possible regularity for these Sobolev spaces? Okay, and so this is our main theorem, which I should write here. So I will write the statement of the theorem, and then I will explain the terms in it for the time that remains. I have 20 minutes. Yes, so I'm good. So theorem, this is joint work with Andrew-Ladakis. I think it's correct. So the theorem says that following. So M at smooth manifold and D a differential operator of order K. Of order K, here I'm cheating. It cannot work with the classical order. It has to work with a slightly different order. But anyway, the following are equivalent. I will explain it in a moment, this different order. So the first one, maximal regularity, but with respect, and of course I have vector fields which satisfy Hormander's condition. For every S, again, I define the Sobolev spaces for natural numbers, but you can extend them by interpolation to real. So for every S in R, for every U, du happens to be in HS, implies that U is in HS plus K. The second condition is a principal symbol, which I will define, which is for every X in M, for every pi in so X, remove the trivial representation. There is a free nilpotent group. I will explain this, but I will write the statement and then explain the terms in it. This function, but you see this pi plays the role of the cotangent vector. This is injective. And the third, again, if M is compact, this is equivalent to for all S in R, d from h tilde s plus k to h tilde s is left invertible modulo compact operators. So we all know that Fredholm is left and right invertible. Here we get only left invertible. It's not that we can't prove right invertible. This is if and only if. So this is as best as it gets. The difference between this situation and what happens for elliptic operators is that here the group is not commutative. Okay, so you see here it's injective. I don't suppose that it's surjective. Okay, so hypoellipticity is also a passage which is left invertibility because you start from du and you go to u. That's a left invertibility condition in some sense. So you get only left invertibility because the group is not commutative. Okay. So I will start with the simplest observation one can make using Hormander's condition. So here we will go back to the remark by Kohn. Here I suppose that the number of Lie brackets, I can use as many as I want. The number of Lie brackets I need is locally bounded because if I have vector fields which span a tangent space, they span it in a neighborhood. And since hypoellipticity is local property, I can as well suppose that I have some bound. So suppose fix n big enough such that I only need n Lie brackets in Hormander's condition. Okay, so the first observation you can make is that every differential operator, because of Hormander's condition, every differential operator, you can write it as a polynomial in the vector field, non-commutative, of course, polynomial. P is non-commutative with coefficients in C infinity of M. Why is this the case? This is very simple to see. So a Lie bracket is by definition a non-commutative polynomial. And so iterated Lie brackets are also non-commutative polynomials. So Hormander's condition tells you that any vector field, you can write it as a polynomial, of course non-linear, of the vector fields. And since any differential operator is a polynomial in the vector fields, this holds. Okay, and so we get to the definition. The Hormander's order is the minimum degree of this polynomial. It can be bigger than so. Hormander's order is equal to minimum degree of P. So for example, if you go back to the example we had with Folland and Stein, where I used these two Hormander's vector fields, dy, I cannot write it as a linear combination. Best I can do is a commutative. So this has Hormander's order order 2. Okay, maybe I should use this and keep it. And of course, the reason why we use Hormander's order is very natural. If D has Hormander order k, then it extends to a bounded operator from hs plus k to hs. It doesn't work with the classical order. This only works with Hormander's order, because that's how the vector, the Sobolev spaces are well defined, are defined. And so this theorem is just silly if I use the classical order. Okay. So I define the Hormander's order. What remains is to define this state, the group, and there is a group and there is two x and there is a principal set. So the first thing you notice is that Hormander's condition So the first thing you notice is that Hormander's condition is satisfied in different ways. What I mean by this is the following. So if you look at these two vector fields, if x is non-zero, then I linearly span the tangent space. I don't need to use any commutator. If I don't linearly span, but that x is equal to 0, I need commutators. Okay? And so the easiest way to get around this difficulty is to use a group, free nilpotent group, big enough that it projects to every possible situation that can happen. And here is where the condition, this condition is important. The only way I can make the group finite dimensional is by bounding the number of D brackets I need. So this idea, yeah, I should say here. So this theorem comes after work of many people. There are a lot of people who work on this topic. As I said, the starting point is Hormander and Stein, then there is Rothschild and Stein, Helfer and Noriga, Mellin, Christ, and others. I will probably not have enough time to give, and Ponge, and Van Erb, and Juncken recently. And this was a conjecture by Helfer and Noriga from '79. They proved the implication 1 implies 2. So they give the necessity of this principal symbol, but they didn't prove what you would want, which is that this is actually sufficient. And they don't talk about 3. They don't work with C-star algebras, so they didn't talk about 3. But it turns out, as I will explain in the time that remains, that 3 is the key point to proving this. This can only be done using C-star algebra, to my knowledge. I don't know how to do it other way. So now I want to define this principal symbol. So I take G to be the free nilpotent algebra, Lie algebra, with one generator for each of depths. What do I mean by this? So I take the freely algebra generated with one generator for each one of the vector fields. This takes all Lie brackets, and the only thing you have to respect is Jacobi and antisymmetry. And then any Lie commutators which have more than n, strictly more than n commutators, you just divide by them. That's a finite dimensional vector space, finite dimensional Lie algebra, and it's very well studied in Lie algebra theory. So it exists. So I can take G to be the simply connected group, integrating G. Okay. Quick remark: this is nilpotent Lie algebra. So the Baker-Campbell-Hausdorff formula is a finite sum. So you don't really need to. This is not an abstract group. It's just the space G. You can take it as a space G with the product. Now, these covectors, the things which replace cotangent vectors, are irreducible unitary representations. So you take phi, an irreducible unitary representation of this on some Hilbert space H. Okay, and so I have a point. So I have a point x in M, and I have an irreducible unitary representation. For the moment, there is no relation between x and M. Of course, in the classical case, phi would replace the cotangent vector. For the moment, there is no relation between x and phi. And using this, I will define the principal symbol. So how do I define the principal symbol? The first step, if you recall the definition of the classical principal symbol, you write it in local coordinates. And then you replace, you do the usual trick, cut off lower order terms, and then replace xi with dxy, dxi. So the first step, I write it in local coordinates. By this, I mean I write it as a polynomial in the vector field. These are my local coordinates. What do I do? Then the principal symbol of x and phi what will this be? So I do the following. P with a polynomial. So the first thing is I do, just like the classical principal symbol, cut off everything of lower order. Okay, the second thing I do, replace every coefficient with C infinity. So the coefficients are C infinity functions, just replace them with the value of them at the point. Okay? What do I do with the vector fields? My representation, I can differentiate it. And so I can obtain a map from these to linear maps on C infinity vectors. And so I can just put this. And so this becomes a linear map from C infinity vectors to C infinity vectors. Okay? Now you come to the obvious question. That's an excellent question. That's actually the questions that Helfer and Noriga didn't ask, and that's the key to solving this. So the problem is that you don't know this. For the classical principal symbol, you can replace. It's very easy to show that it doesn't depend on local coordinates. But here, it's much harder to see even why, if you take another polynomial, this doesn't depend. And actually, it depends on the choice of the polynomial. But the key point is that for every x, there is some representations, which I will, in the time that remains, try to explain where they come from C-star algebras. And this set, for this set, it's well defined. For every x in M, there exists a theorem. Again, the same authors. For every x in M, there exists some set of representations, which always contains the trivial representations, because such that this is well defined. Okay. So I wrote almost all of the things in the theorem. I just didn't tell you what this set is. It will appear very naturally once we do the proof of this theorem, which I will try to explain the ideas of it in the last time that remain. So we want to prove this theorem. Now we all know from functional analysis this very simple lemma. If you don't know it, it's an exercise. If T is a map on Hilbert spaces, T is left invertible if and only if T star T is invertible. Okay? And so since invertibility is a much easier condition to deal with than invertibility, here we'll do the same thing. So we'll actually prove. Yes, yes. So here we will prove a variant of this, but with, I replace D with D star D. Okay? And so here I will get Fredholmness. So if I want to remove it, so the variant, which is D star D, here it will be Fredholm. Here it will be bijective. Here it will be, this condition is satisfied, and D star U implies H tilde S implies U is in H tilde S plus K. The same condition is satisfied for this adjoint. Okay? So it's equivalent. It's very easy to see that if you can prove one of them, you can prove the other. So how do you prove this theorem? I should start here. The first step, you define some calculus, so the first step, I would suppose that M is compact. Okay? It's not actually an auxiliary condition, or to simplify, but actually I need M to be compact to do the proof and then prove it for non-compact manifolds. It will be clear when I do the trick in the end, which I promised you at some point. So the first step is you define a pseudo-differential calculus. So these are operators. If P is here, then P acts from HS to HS plus K, HS plus K to HS. and they have the usual formulas. They are closed under a joint. They form an algebra. If P is in psi 0, then P from HS to HS is bounded. From L2 to L2 is bounded. And also from HS. And if P is in psi negative, then it's compact. Okay? But the two key properties I don't have. The principal symbol, we already say that this is complicated for differential operators. The problem, I can define it. The problem is that I can show that it's well defined, that it doesn't depend on the choice of the symbols that I use to construct the operator. Parametrics, that's also a problem. The problem here is as to explain why this is a problem, the parametrics. The way these operators are constructed is using the group, okay? The group has much higher dimensions than the manifold. Essentially, if I can construct a parametric on the group, I can project it and create a parametric on the manifold. Okay? But that works in one direction, doesn't work in the other direction. So actually, what we can use work of Rothschild and Stein and Helfer and Noriga, you can actually show quite easily that for every k, so these are defined for all k in R, even k in C, but I only need them for every k in R, there exists one operator, which I will denote it by pk, which has a parametric. I don't know how to construct parametrics for all operators, but I know that for every order there exists at least one. And I really need k in R for the trick at the end. Okay? Now, here is where, so as I said, I don't know how to do, how to construct parametrics. And if one could construct parametrics, Helfer and Noriga, who are experts on those type of things, would have probably succeeded at doing it. So instead, we'll study C-star algebras. We know that the operators of order 0 are bounded, so I can take psi 0 bar, the closure of this, that's a C-star algebra, and of course it contains compact operators. And so if I want, so what I will study is this condition, Fredholm's. By Fredholm's amounts to invertibility here. So yeah, I should say a remark I forgot to say. So this thing here allows me to reduce this statement to operators of order 0. Okay, so I should only care about what happens for operators of order 0. Okay, right. Anyway, so I want to know when an operator of order 0 is Fredholm. That's the third condition. That amounts to invertibility of this thing here. By Gelfand's theorem, that amounts to invertibility in every irreducible unitary representation. So all I have to do is study the irreducible unitary representations of that C-star algebra. So a theorem by Clotilde, so if you call this C-star algebra a theorem by Clotilde, Fermanian, and Veronique Fischer tells you that its irreducible unitary representation have to be a closed subset of this space, M cross, so for every, no, sorry, so a closed subset of M cross G hat. That's correct. Okay, so it's some set of representations of your group parameterized by X. Of course, you all know that in the classical calculus, this is a cotangent bundle. Okay, so in the classical calculus, the representations are everything. Here, they don't happen to be everything, but we don't know which ones are they. Okay, but here is an important remark. When is the principal symbol well defined? But obviously, it's defined for these representations. All I have to do is take the by symbol, put it here, then apply the representation. So I know that for some set of representations, it's well defined. I just need to compute this set. Okay, but even if I don't know how to compute it, I get for free theorem. The following are equivalent. For every k, for every x and phi in this set, so I call this set tau x. Okay, except the trivial representation. Why I bought tau x? Because I don't know whether it's uniformly the same set. Okay. This invertibility condition is bijective. This is equivalent to P from L2 to L2 is Fred. This is just free. Okay. I have to say a small remark. Here is bijective is a little bit, you have to be careful here. So here, when I said bijective, it's bijective on smooth vectors. It's not trivial that bijectivity on L2 is equivalent to bijectivity on smooth vectors. That's a theorem. Here we use the theorem of Helfer and Noriga. Okay, but it is true that if you have bijectivity on smooth vectors, that's equivalent to bijectivity on L2, and then by Gelfand results, you have this. Okay. I should keep this. I can remove this. What? Yes, of course. So I said that M is compact. I need it in multiple places. One of the places that this is unitar. Now the proof amounts to two parts. The first part is that Helfer and Noriga gave a formula for this tau x. So I need to compute this tau x and show that A hat is this. This is a part which I cannot really do in the -2 minutes I have. And so I will just explain the idea. You construct a variant of Constantine groupoid. So Constantine groupoid, here you have Tm at 0. That's the dual of tau x in the classical calculus would be the cotangent space. Okay? So the idea is that you take the set that Helfer and Noriga conjectured, and you construct, I will put this, it's essentially the dual of this set. And you construct a groupoid like this. Okay? It's not really constructed this way. You have to blow up the set of representations. That's a different story. Anyway, you construct this groupoid, and then Dabor and Skondali tell you that if you have this groupoid, then its C-star algebra is essentially Morita equivalent to the C-star algebra here. So the representations of the C-star algebra of the groupoid are your representations. And then Renault's theorem, which tells you that representations of the C-star algebra come from the groupoid structure, both of them tell you that A hat is equal to this set, the one that Helfer and Noriga defined in a much more elementary way without using C-star algebra. Now we are in a Bosonic situation. So here is where the trick comes. So I'm in an opposite situation to what happens with Atiyah and Singer. So Atiyah and Singer, when they worked on the index theory, they had the classical pseudo-differential calculus, they had ellipticity theory, they knew that the solutions of their equations are C-infinity, they just need to compute the index. Here I'm in a different situation. I know that the solutions are finite dimensional, but I don't actually know if they are smooth or not. Okay? And so I can do index theory, I can do K theory and so on, but I don't actually know how to construct a parametric. The trick, you don't need to, you are almost done with the proof. So the proof is as follows, the trick is as follows. I need to here. Here I had the statement for L2, but I had a parametrics for every K. So if I replace the operator with pk minus 1, so replace p with pk, p minus k. Then this theorem, by applying it to this, I actually get for free the Sobolev spaces. Now I'm almost done. All I have to do is compute the Fredholm index. So I take my operator from HK to HK and satisfies this condition. I know that for every K it's Fredholm. Okay? And since K is real, I said in the beginning, I need K to be real. The Fredholm does not change. So Fredholm index is constant. But what is the Fredholm index of this operator? It's dimension of the kernel. It's the kernel intersection HK. Here I say the kernel as a space of distribution, and then you intersect with HK. Minus, I use the formula that the Fredholm index is the dimension of the kernel minus the dimension of the kernel of the adjoint. What is the adjoint of this operator? Well, its adjoint is P star. This is the formal adjoint. So that would be the adjoint when you act on L2. But here I act on HK, so the adjoint would be this. We'll have to flip minus K. So it's minus dimension of the kernel of P star intersection H minus K. And this is constant. I don't know what the constant is, but I know that it doesn't depend on K. 1 minute. Sorry. So what do I do? Well, the Sobolev spaces are included in each other. So this is a decreasing function in K. This, by the exact same argument, is an increasing function in K. And so with minus, this is also a decreasing function in K. So I have a decreasing function plus a decreasing function. That's constant. The only way this can happen is if both of them are constant. And so I get the dimension of kernel of P intersection HK is constant. But the only way this intersection is constant if the kernel was in all of the Sobolev spaces. Otherwise, it has to jump at some point. And so the kernel is in the intersection of all of them, but that's just the infinity function. And the same for the adjoint. And so my operator, I show that it's Fredholm, which means that it's invertible modulo the kernel and the co-image. And I show that these things consist of the infinity function. That's my operator preserved Sobolev regularity, and that's done with my talk.